the goal of today is to wrap up this exploration, which is to say that if we define a relation on the integers by x is related to y, if the difference between x and y belongs to a set A, okay, then what qualities of that set A are necessary in order to make this relation respectively reflexive, symmetric, or transitive? And when we left our last class, your groups were kind of in a variety of stages of figuring out either how you want to answer this question, so what quality of the set A do you want to fill in that blank? And then if you did figure out what you wanted to put there, the next step is to try and write up a proof. So what I'm going to do as we get started here, to get your group started, is to give you another big white piece of paper that's going to go up on the wall at the end of the day. And if you're ready to start writing out your proof of this, that's great. If you're not, and you need a little more time to think through the property of the set A that you want to have, I saw some great discussion happening in Group 10 on Slack over the last couple of days, so I can see that there's been some progress made in answering this question since our last class. If you're ready to start writing up this proof, then you'll be able to do that. If you need a little more time to talk things through first, you'll have that time also. And then, as I said, in about a half an hour, we'll shuffle up to your card-suited groups to figure out what we learn across all three of these different properties. The one thing I want to say about proof is that the claim, the assertion that you're making here, has this conditional form. Right? If A is a set that satisfies some property that you're deciding on, then you need to be able to show that this relation satisfies the reflexive property or whatever property it is that you're looking at. So if that's the claim that you're trying to prove, what do you think your proof is going to look like? What structure is this proof likely to have? When you prove an if-then statement, an implication, a conditional, what does that proof tend to look like at a 30,000-foot view? What are some of the key things that you would be looking for? So one strategy for proving a conditional statement is to take the assumption, the hypothesis, this thing here at the beginning, the thing that comes between the if and the then, take that as an assumption. So this is strategy number one. Assume A has whatever property that you decide it needs to have. And if you make that assumption, what do you then need to show? What is your burden of proof? And I'm going to encourage you to write down your burden of proof so that the reader knows exactly what it is that now you need to deduce. So if you assume that A has this property, what do you then have to prove? If P, then Q. Assuming P, what do we have to deduce? Q. We will show that this twiddle has the whatever property, right? Whatever property your group is working with, reflexive property. What is this strategy of proof called? Remember from your transitions class? Yeah, this is a direct proof. Why is it a direct proof? Right, so we're proceeding directly, if you like, from the hypothesis to the conclusion, right? We're proving the thing in the same order that we read the thing, right? We assume P, we deduce Q. What would be the alternative to that? If a proof is not a direct proof, what kind of proof is it? Well, it's indirect. So what would an indirect proof of this if P then Q look like? Yeah.
To assume Q.
Assume Q. So assume that twiddle has the reflexive property. What do I then have to prove?
That if A has its property proved true.
We want to show. So in other words, assume Q and then prove P. We want to show A has whatever property. What do you all think of that as a strategy for proving if P then Q? Right. So on the one hand, we have the thing we're trying to prove is if P, then Q. That's the original statement. P implies Q. This is our burden of proof. And so a direct proof has the structure assume P, deduce Q. That was the first one we talked about. But then you've also surfaced two other conditional statements if Q, then P, and if not Q, then not P. So my question to you is, one of these two conditionals is equivalent to P implies Q. Which one? It's the second one. What's the name of that second one? Contrapositive. So the contrapositive of a conditional statement is logically equivalent to the original. If one of them is true, the other one must be true. So these two conditionals are equivalent, which also means we can prove one of them by proving the other. On the other hand, what is Q implies P called? It's another word that starts with C. Close. It's the other. It's one. There's one other word that starts with C. I feel like I'm playing hangman now. Converse. And the converse of a conditional statement is not in general logically equivalent to the original statement. They are totally distinct. For example, we might say, if I am a square, then I am a rectangle. That's a true statement. If I am not a rectangle, then I must not have been a square, right? Those two, each of those is true because the other one is true. Right? On the other hand, if I am a rectangle, then I am a square, not so much, right? Sometimes a statement is logically equivalent to its converse, but in that case, it's not just a conditional, it's a biconditional. Those are the if and only if statements, are the ones in which those two are both true. So this is not a valid strategy. Not a valid strategy to prove P implies Q, because the converse is logically independent from the original statement. But the contrapositive suggests a method of indirect proof. If I want to prove this statement, what would I assume and what would I deduce? Assume not Q. So assume Q is false and deduce not P. That would be an indirect way to prove this statement, or you might think of it as a direct way to prove the contrapositive. Right? And then there's one other C word that we mentioned along the way as the third type of strategy for proving P implies Q in an indirect way, and that's contradiction. So in a contradiction proof, what do we assume? And what do we deduce? This is the most fun for mathematicians, I think. At least for me as a mathematician, this is the most fun form of argument.
Don't you assume the opposite of Q?
You assume the opposite of Q, but you also assume one other thing.
Assume P and
Yeah, we assume two things. We assume P and the opposite of Q. So what we're doing when we start a contradiction proof is we're setting ourselves up for failure, basically, when you start a contradiction proof. Because the assumption that P can be true and Q can be false, that's really what we're saying here. Assume P holds, but Q doesn't hold. That's exactly the assumption that our original implication is a false implication. Right? The only way to show that P does not imply Q is to demonstrate that it's possible for P to be true and for Q to be false. If somebody claims that if I am a rectangle, then I am a square, if I want to prove them wrong, I need to find an example of a rectangle which also is not a square, right? So I'm turning the truth value of this implication on its head when I start a contradiction proof. The other nice thing about a contradiction proof is it gives you more material to work with because you get to make two assumptions. You get to assume that P is true, and you get to assume that Q is false. So sometimes contradiction just gives you more to work with. And then what do we have to deduce in a contradiction proof? We have to arrive at a contradiction. And the problem with contradiction arguments is that we don't always know what it is that we're going to end up contradicting. But the basic logical content of what we get when we finish a contradiction proof is that we show that if it's true that P can be true while Q is false, right, if we make that assumption, we have to show then that there is some other statement, we'll call it R, which is both true and false simultaneously. Right? And because in the structures of logic, the way that we do ordinary logic, not fuzzy logic, every statement is either true or false and cannot be both. If we can deduce that R is both true and false, so R is true and not R is also true, then that must mean that our original assumption was flawed. So hence, not quantity P and not Q. And that's, again, logically equivalent to P implies Q. So contradiction proof is kind of the third strategy for these. It gives you more to work with, and it lets you sort of play around, but you don't always know up front, you usually don't know up front, what exactly it is that you're going to be contradicting. And so as soon as you arrive at something that is patently absurd, you can say, okay, great, we've arrived at a contradiction from our original hypothesis, and our hypothesis was that this was false. Therefore, since this being false implies something absurd, this must be true.